In the last lecture we discussed about the Reynolds number, and we said that Reynolds number is the ratio of two different kind of forces, inertial forces and the viscous forces, and there will be dominance of one kind of force. If inertial forces are predominant, then in that case the perturbation or disturbance at any point will not distribute and it will get accumulated at any point, which leads to the problem of instability. On the other hand, if viscous forces are dominant, then the perturbation or disturbance at any point will tend to distribute from one point, and there will be no any accumulation of the disturbance at any point, which leads to the stability. And also we discussed about the various examples, like if the water is flowing from the tap and it is in the low Reynolds number region, then if you pinch the flow of water by using some pen or your hand, you see that water again gets stabilized. Or if the laminar flow is happening in some kind of field or plane, if you see, then any kind of disturbance is not going to make it chaotic, just because the viscous forces are more dominant in that flow. And we have seen the example in which if the flow is very fast, in the case of tap as well, if the flow is very fast, if we introduce any kind of disturbance, it will tend to make the flow chaotic. The disturbance, a small disturbance that we have made, will create a chaotic motion in the flow, and due to the introduction of that disturbance, it will grow into further larger disturbance, and that large disturbance will grow onto further larger disturbance, and in this way we can have a complete chaotic flow in the case of dominance of inertial forces. Okay, after that we discussed some examples. The first example was related to the mass pulley system, in which there is some liquid which is placed at the bottom of mass m1, and we had to find the velocity as a function of time for the mass m1. We did some force free body diagram on the different masses in pulley, and we tried to evaluate the velocity as a function of time. The next example was there, in which we had two different concentric cylinders, and we wanted to evaluate the torque which is required to drive the cylinder. So the torque is required because there is relative velocity between the two layers, starting from radius is equal to r1 to radius is equal to r2, and at any section at small r between r1 and r2, you will find that there is a velocity gradient present, and because of the velocity gradient, the shear stress is present, and if you multiply that shear stress with area, we can find what is the force which is required to drive that particular cylinder, which is located at a radius r from the center. And note that it will vary from r is equal to r1 to r is equal to r2. So we take a small element at r is equal to capital small r, and we try to find the torque, then force, then what is the stress, then force, and then torque. And we integrated that equation from r is equal to r1 to r is equal to r2, as that is a variable. In this fashion, we evaluated the value of torque required to drive the concentric cylinder in which the fluid is filled in between. The third example was associated with the piston type circular object is rotating on a surface, and the points which are closer to the axis is rotating with the speed which is much lesser, and because of that the gradient which is created is much less. As we go away from the axis, the velocity of the piston in the theta direction continues to increase, and it is given by omega r. So the difference in the velocity between any point on the piston to that of the surface will increase. So if the velocity difference is increasing and height between the piston and the surface is kept constant, the velocity gradient will certainly increase. So this was also a variable problem, and we discussed this problem in the last class. The next problem that we discussed was of surface tension, in which we introduced the concept of cohesive and adhesive force, the force applied by the molecules from the surrounding on a molecule. So it was a force which was applied. If a molecule is present at the surface, it experiences different kind of forces from the top and the bottom, which leads to net inward force on the molecule, but still it is stable surface. This means that there is some kind of energy associated with the surface molecules, and that energy per unit area is called as surface tension. Also, we introduced the concept of force per unit length on the surface is called surface tension. Then we derived the Young's equation just by the balance of the surface tension in x direction, and we moved on to the concept of how surface tension is correlated with that of the delta P. If our surface ABCD is extended to A prime, B prime, C prime, D prime, and the radius of curvature associated with AB and CD is given by R1, and radius of curvature associated with A prime, B prime and C prime, D prime, which is same, is given by R1 plus delta Z. In that case, if I extend the surface from ABCD to A prime, B prime, C prime, D prime area, then what is the work done by pressure forces given by delta P into the area of ABCD, which is given by XY into delta Z. And the work done by the surface tension is given by total change in the surface energy associated with the two surfaces. So we equated these two equations in order to get the relation between delta P and the surface tension. After that, we introduced the concept of rise of liquid in column, in which we introduced the concept of surface tension that we discussed earlier. So because of that, one concept here I would like to explain, which I forgot to mention in the last class, about surface tension. Suppose this is the surface. I am just trying to explain this, why the rise of the liquid happens in the capillary. Suppose this is the surface and this is something capillary which is introduced in the liquid. This is the liquid. This is the bulk liquid or bulk liquid. Now because this is a glass and bulk liquid is water, there will be some kind of interaction between glass and water, which leads to, this is the intrinsic property of glass and water, because the surfaces of the water at the interface will interact with the molecules of glass, and because of that there will be some kind of attraction or any kind of different kind of force will be acting, and because of that there will be formation of meniscus like that. This is due to the interaction between the molecules of water and the molecules of liquid. Now there will be difference in pressure at point 1 and at point 2. There will be difference in pressure because of the formation of this meniscus. Okay, and how much is the pressure difference from 1 and 2 is given by the equation of by the equation that we derived, how delta P is related with surface tension. So the pressure at 1 is given by PATM, and pressure at 2 is something P2. Okay, pressure at 2 is something P2. Now P1 is greater than P2, and let us say I have this point 3 which is exposed to the atmosphere. So this pressure at 3 is also given by PATM. Now you can see there is point 2 and point 3 which is existing on the same horizontal line, and the pressure at 2 is much less compared to that of pressure at 3. So in order to balance the pressure at point 2 or pressure at 2 to make it equal to pressure P atmospheric, the liquid will rise, and it will rise to such a height that the pressure at point 2 will become equal to PATM. So suppose after the liquid rise, how it looks after the liquid rise, this is the surface and it will reach to some height here. Now this is point 1, this is point 2, and this is point 3. Suppose this has lifted or rise, the rise is given by H. So how I can know pressure at point 2 is given by the pressure which was decreased, so I will have to add a pressure rho g H. Okay, suppose this is, let us say this is 2, this is 2 prime, so P2 is equal to P2 prime plus rho g H. Now sorry, this is P2 prime is equal to P2 plus rho gh. Now the pressure at point 2 prime, after the liquid or capillary rise has happened, because of that the pressure has at point 2 prime becomes equal to pressure at 3, and this will be P2 prime is equal to P2 plus rho gh is equal to P3 is equal to P8m. Just in order to maintain the pressure at any horizontal line to be same, the liquid rises in the column, because due to the formation of meniscus there existed a pressure difference, and at the same horizontal line there should not be any pressure difference, so liquid will rise in order to increase the pressure at that point, so that the pressure at any horizontal line becomes equal. Okay, this is the way in which you can think. This was the explanation that I forgot in the last class, so I wanted to discuss this here. The next was, if the liquid is not rising and it is falling, in that case what we do is we usually draw the tangent at the point of contact from glass or any capillary tube and the liquid. So if this angle is given by, since this is tangent, so if this angle is given by theta, then the angle made by the tangent with that of the capillary is given by 180 minus theta. So this was the angle that we used in the last formula. In the case of cos theta, we use this formula. The angle theta, as you can see here, this theta angle is the angle which is made by the tangent with that of the capillary. So in the same way here also, in the second case, we will use this. If we use this angle as theta, then this angle will be equal to 180 minus theta, or you can say this angle theta is represented by some 180 minus phi, then this angle will be represented by phi. In the case of, if you consider the angle phi, then delta p will be given by delta p is equal to 2 sigma cos phi divided by r. So this was the basic thing that I wanted to add in the last class lecture. Now I will move on to the lecture on fluid statics. Okay, so let us start with today's topic, fluid statics. In this lecture of fluid statics, suppose I have a tub, and inside this I have kept some water or any kind of liquid. So this is kept still. In fluid statics, this is kept still, and suppose this is direction x and this is direction y. Okay, this is direction x and y. Now I have taken a control volume inside, and the shape of the control volume is rectangular, and I want to draw this in enlarged view. So this is cuboidal control volume, which looks like a rectangle from here. So suppose this length is given by delta x. Sorry, delta x, and this length is given by delta y. Okay, this length is given by delta y. So what is the force acting here? Suppose I want to now I will try to explain the motivation behind what we are going to do. The motivation is, we do want to do a force balance, and then if we want to obtain a differential equation of pressure. Okay, so in the direction x, in the direction y, and in the direction z, we will try to balance the force, and let us see what we are going to get. Okay, so we will consider two kind of forces. The first is the surface force, and the second is the body force. Okay, so let us say sum of all forces in x direction is equal to mass into acceleration. This is something which we get from the Newton's second law. This is not the Newton's second law. Note that the Newton's second law states that the rate of change of momentum, linear momentum, is directly proportional to force. But the ultimate conclusion of Newton's second law can be written in this form: summation of all forces equal to mass into acceleration. If someone asks you to define what is Newton's second law, that is not force is equal to mass into acceleration, but it is rate of change of linear momentum is proportional to force. Okay, so let us try to understand in this summation of all forces, which include F surface means surface forces associated plus F body means body force associated is equal to mass into acceleration. Mass into acceleration. Okay, so what is the surface force? So the force acting on the left face is given by, because it is static fluid, so there is no any kind of relative motion between the two layers which may exert force. It is completely at rest because we are studying fluid statics. So suppose pressure is acting at the left face, which is given by pressure into delta y. This is the force, because in the depth delta z we are considering to it to be equal to 1. Okay, so what is the force at this surface in the opposite direction? It is given by, let us say this is delta y, keep it here. So what is the force? P, we will Taylor expand, P plus del P by del x into delta x. This is the pressure at so let us try to write it further. Okay, let us try to do it in more detail. Okay, what is pressure at x plus delta x? So if we Taylor expand this particular equation for small delta x, I can write px at x plus pressure at x plus delta x is equal to px plus del p by del x into delta x divided by 1 factorial plus del square p by del x square into delta x square by 2 factorial plus summation of other terms. Okay, so we will consider only these two terms and we will neglect the higher terms, and in that case our pressure at left at the right face will become equal to p plus del p by del x into delta y. Okay, this is something we obtain. Now since we have obtained this p plus del p by del x into delta y, so let us say body force per unit mass is given by bx, that is in the x direction. Okay, in positive x direction we may assume. So in the case of surface forces, there are two surface forces acting on the body on the control volume that we have considered. One is acting on the left surface and the other is acting on the right surface. So the first surface force is given by p into delta y. The right hand side is taking, this is the convention that I am using. Okay, you have to keep it in mind, because the force acting in the x direction is given by p into delta y, and the surface force acting the next surface force is p plus del p by del x into delta x whole multiplied by delta y. Note that I have kept this minus sign just to represent that the force at the right face is acting in the negative direction, plus body force. The body force is given by body force per unit mass into density. Density is mass per unit volume, so this gives body force per unit volume into volume is given by delta x into delta y into the depth is 1. Okay, is equal to what right hand side explains, that is mass into acceleration. So mass is given by rho into delta x into delta y into delta z is given by 1 into acceleration, mass into acceleration. This is something we obtained. Now just writing p into delta y minus p into delta y minus del p by del x into delta x into delta y plus b rho into delta x into delta y into bx is equal to rho into delta x into delta y into ax. Now p delta y gets cancelled and we divide the entire equation by delta x delta y, that is given by minus del p by del x plus rho into bx is equal to rho into ax. This is something we obtain. This is the consequence of the balance of force in x direction. Similarly, I can write it in y and z direction, that del py del y plus rho into body force in y direction is equal to rho into acceleration in y direction, and del py del z plus rho into bz is equal to rho into az. These are the other two equations which we can obtain. Okay. Now, suppose I have a free surface and you want to find what is the pressure difference, because we know the equation, and we want to apply this equation in order to get what is the pressure difference between two different points located at a height h, or the difference in height is h. This is the free surface, okay, and I want to find what is the pressure difference at a point which is located at two different locations 1 and 2, and the height is given by delta h, or this is something given by z1 and this is given by z2. Okay, so this is the direction z, this is the direction z, or say this is the direction x or something. Now minus del p by del z plus rho into body force per unit mass is given by g, mg divided by m is given by g, and I assume there is no acceleration in the z direction, so the right hand side comes to be equal to 0. So dp is equal to, or I can write this as minus of dp by dz is equal to minus of rho g, or I can say dp by dz is equal to, or dp is equal to rho into g into dz